Hey, so this is Joe, and this is the first video for Chapter 6 in Stewart's Calculus. And here I'm going to be talking about inverse exponential and logarithmic functions with calculus, and basically giving you and then applying a bunch of new differentiation formula that we have for some new functions. Now, your book spends a lot of time going over things like how to graph exponential and logarithmic functions, properties of logarithms, properties of exponential functions, how to take the inverse of a function. And if any of you are having trouble with that or need a refresher, look at our Sullivan and Sullivan pre-calculus textbook videos, and you should be able to get some help with that and then come back to this video, because I'm not going to go over that stuff here. Instead, so the main thing I'm going to be doing with this video is basically showing you how to apply a lot of the formula that are presented to you in the book. But before I do that, because this chapter is so long and there's a lot of stuff that you'll probably remember from previous courses, I'm just going to highlight the new stuff really quickly right here. Alright, so first we have this little identity that it doesn't come in handy too often, but conceptually it's pretty easy if ever you have to deal, or helpful I should say, if ever you have to deal with inverse functions. So an inverse function, it's where you have a function in terms of y and x, and basically you do a one-to-one matching of all the y's for the x's and basically flip them. And there's some fancy ways you can do that. Not very fancy, but you did that in pre-calc. However, let's say you want to take the derivative of an inverse function. Well, you could always just find that inverse function and take its derivative, or if it's tough to take the inverse function, what you can do is you can say that that inverse function, the derivative, is going to be equal to 1 over the derivative of the function, the original function itself, but you plug in the inverse function into that function, and so you kind of re-switch the variables. And intuitively that makes sense, because if we write things out like the derivative of y with respect to x, that's equal to 1 over the derivative of x with respect to y. So you just need to put everything in x's, take the derivative with respect to y, and then invert that, and you'll get the derivative of y with respect to x, where y is the y of the function, the inverse function. So 2, we've got a very important differentiation formula, which is that the derivative of e to the x, and e is the natural exponential function, is equal to e to the x. And this is what makes e to the x and natural logarithms, which is a logarithm with a base e, so special, because the slope of e to the x, all the slopes are equal to the values of y. Its derivative is equal to itself. So that's what makes this so handy in terms of dealing with other more difficult functions to differentiate. And so just bearing that in mind, we have 2 more definitions of e which come in handy when we're solving limits. E is equal to the limit as x approaches 0 of 1 plus x to the 1 over x. So if ever you see that in a limit, you know that that equals e. That's just something you should memorize. And then this is why it's because of this limit that e is so important in finance, that e is equal to the limit as n approaches infinity of 1 plus 1 over n to the n, is e is used in computing continuously compounded interest, and it's used for that because e is the number that occurs when you continuously multiply this quantity. And so you can make this number really big and continue to multiply it by itself, and it'll always converge at e. And we'll explain more. That sounded kind of confusing, but it'll come in handy, I think, later in this chapter or the beginning of the next chapter. Now, the next differentiation formula is for logarithms, general logarithms with the base other than e. And so the derivative of that is 1 over x times the natural log of whatever was in the base. And that's because of this identity that the log base a of x is equal to the natural log of x over the natural log of a. Now technically, this natural log could be a log with any other kind of base, technically, but that would make so much algebra and all these other formula so much more difficult. So that's why we use the natural log. Now, the reason we use the natural log is because of this, that you take the derivative of the natural log and it's only equal to 1 over x, because the natural log of e is 1. And remember, natural log is a log with the base e. So, two properties that are important to memorize and just remember and bear in mind when you're solving problems with logarithms and with natural exponential functions is that e to the natural log of x is equal to x, or for that matter, any number to the power of a logarithm at the base of that number is equal to whatever is inside of the logarithm. And natural log of e is 1. So now I'm going to do some practice problems involving all of these differentiation formula and applying the chain rule to all these differentiation formula. And the chain rule applies to these in the same way it applies to trig functions and all this. If this x, for example, was replaced with some function of x, right there, the derivative would be e to whatever is in the exponent times the derivative of whatever is in the exponent. And that's just how the chain rule ends up working out. And I'm going to write it out more explicitly later. But I hope you see now that the reason, and we're going to be also doing using natural logarithms to kind of break up more complicated functions to take the derivative of them based on the fact that we're able to based on some of the properties of natural logarithms, but we're going to be using specifically natural logarithms instead of logarithms with the base of something else, just because doing calculus with them is so easy because of the fact that the derivative of e to the x is itself, and that is why we're going to be using natural logarithms as opposed to other logarithms so much more. So before we go on to solve some more problems, I just need to show you this one last differentiation formula, which can be derived from the previous one for the derivative of a logarithm with a base a. But if we're taking the derivative of a function where it's some constant to the power of x, or some function of x, the derivative is the original function times the natural logarithm of the constant, the base right here, and then should this x actually be a function of x, based on the chain rule, you'd multiply everything by the derivative of that function. Alright, so now for the problems. Alright, so number 17 on page 418 in your book asks us to differentiate this formula, f of x equals x to the fifth plus 5 to the x. So, the first term, we've been doing this for a while, that is 5x to the fourth, because the variable is in the base and the exponent is a constant. Now we're going to have to use a new differentiation formula for this one. So we have the function, we write down the function itself again, and then multiply it by the natural log of the base, and so that's 5. So that is the derivative. However, let's break off from the book a little bit and make this x a function of x. Alright, so let's say we define a function g of x to equal 2 to the x, and then we redefine f of x up here to be f of x equals x to the fifth plus 5 to the g of x. Now let's apply the chain rule to solve that. And remember, the chain rule, even though there is a longer form of substitutions that we can make, all you have to remember when you're actually solving these formula or these problems is that you have to keep if there are more functions in specific places, you need to keep taking the derivatives of those and then multiplying them by the derivative of the greater thing. You have to keep going inside and taking derivatives. So take the derivative of f, we'll still get 5 times x to the fourth plus, let's do the same thing as before. This is an exponential function, so we'll write the function itself again, 5 to the g of x, same as we did up here, times the natural log of 5, but now we have to take the derivative of g, so just times g prime of x, and we can actually substitute in for g of x now, so that's 5 x to the fourth plus 5 to the x times the natural log of 5, and now we have to take the derivative of this. Well, it's an exponential function, so we write 2 to the x times the natural log of the base, which is the natural log of 2. And there we go, that is our derivative. Alright, so now we're going to solve number 9 from page 418 as well, and we'll have to use the product rule and the chain rule here, so it's kind of combining everything as well as a new differentiation formula. So, take the derivative of f, and we have these two functions that are multiplied by one another. So, we'll take the first one, take the derivative of it, leave the second one alone. Derivative of sine is cosine x times the natural log of 5x. Plus, now we leave this one alone, we leave the sine x alone. You take the derivative of this, which is 1 over whatever's inside, 5x, but because 5x is a function and we can take the derivative of that, and it's something other than 1, we take that derivative and make it a coefficient, and so we take that 5 and put it out here, and that is that derivative. Alright, so now we're going to do problem number 45, which requires us to use a technique called logarithmic differentiation, which is actually the reason why natural logarithms are so helpful in calculus, and why they're such an important function to be able to deal with, because they help us break down nasty looking functions like this one. F of x equals y, which is equal to the square root of x minus 1 over x to the fourth plus 1. That's a really ugly function. We've got a radical, we've got a quotient, we've got x's in both terms. It's a mess. We need to do a ton of substitution, a ton of work if we weren't to use this technique. So, in the same way algebra, you can add the same thing to two sides of an equation. You can take the logarithm of both sides of an equation. In this case, we're going to take the natural logarithm of both sides because they're easier to deal with in terms of taking derivatives and integrals and calculus in general. So we're going to get the natural logarithm of y, and remember that the object of this is to get f prime of x, or y prime, so the derivative with respect to x, is equal to the natural log of that function's x minus 1, x to the fourth plus 1, all square rooted. So, first off, we can use our properties of logarithms to get rid of a lot of this stuff. So the entire argument of the logarithm is to the power of 1/2. So we can bring a 1/2 out here, and then the logarithm of a quotient like that is actually one logarithm subtracted from the other. Specifically, logarithm of x minus 1 minus the natural log of x to the fourth plus 1. And that's all equal to the natural log of y. But we need to get y prime out of here. Well, we can do some implicit differentiation if you remember how to do that. So that, when we take the derivative, is equal to the derivative of y, chain rule, over y, because the natural logarithm of 1 over x, right? But in this case it's y. And we have to have the y prime because of the chain rule. And that's equal to 1/2, can take that out as a coefficient. Now we take the derivative of this, it's 1 over the argument, and the derivative of the argument is 1, so we can just leave it as is, 1 over x minus 1, minus, now the derivative of the argument here is 4x to the third, and that's going to be times 1 over the whole thing, x to the fourth plus 1. Now, we can simplify all this, and eventually we're going to need to multiply this side by y. What is y, though? Because we want this to be a derivative in terms of x. Well, we have an expression for y up here. It's just the original function. So we can rewrite this whole thing as y prime equals root x minus 1, x to the fourth plus 1. And then we distribute that too, and we put everything in parentheses, so you get 1 over 2 to the x minus 1 minus 2x to the third over x to the fourth plus 1. And that is the derivative with respect to x using the technique of logarithmic differentiation. Alright, so I haven't forgot about integration, and remember all of those differentiation formula apply to integration. Just remember, you have to think, okay, given this expression that I need to integrate, what would the derivative of it be? And then you can kind of manipulate those differentiation formula accordingly. So sometimes instead of multiplying, you'd be dividing by one thing, etc. And that's a better way to think of it, I think, than memorizing, like 4 or 5 more formulas. Just memorize the differentiation formula and then apply them to integration and going the other way. And also, you're going to be more likely to make fewer errors because you'll be thinking more critically about your problems. So, with this problem, we're going to need to make a u substitution. Namely, and we've got to see, since there's a fraction here, we're probably going to end up making this some sort of logarithm. So bear that in mind. So we probably want the numerator to end up going away. So let's substitute, let's make this expression u. U is equal to 2 plus sine x. So then du would be, sine is cosine, so du is cosine x dx. Well, we see a cosine x dx, and we see the u in there. So we can write this all in terms of u. We've got du over u. And that looks like something we can evaluate with a logarithm. And so since this is an indefinite integral, we can write it as the natural log of, and be careful now, it has to be the absolute value of u plus c. And we use these absolute value signs because if you picture the graph of a natural logarithm, it doesn't get negative. You can't have negative x values or negative arguments. The argument must be positive. So on the AP, they will take off points if you don't explicitly have these absolute value signs. And so then now we're able to put substitute back in for u. It is the natural log of 2 plus sine x plus c, and that is that integral. Alright, so that's it for this video in the first section of chapter 6. Stay tuned for the rest of the videos where we go more in depth into specific applications of calculus to exponential growth and decay problems. And also, we're going to get to that fancy technique about limits that makes limit solving a whole lot easier that I mentioned back at the beginning of this course. Yeah, so thanks. Stay tuned.